Okay. So we have a circular orb of radius r. We're going to slow down to some velocity v sub I to get closer to the planet. We're going to end up with closest approach at distance a from the center. What's the expression for a? Okay. We begin by analyzing the circular orbit. We have the law of universal gravitation, just the magnitude here, not worried about the vectors in this case. And the fact that the centrifugal force is the gravitational force. There's nothing else to give you the centrifugal force, and you can't stay in a circle unless you got a centrifugal force equal to, and centrifugal acceleration equal to v squared over r, centrifugal force, therefore m times v squared over r. Okay, set those two equal, and you get the velocity. All right, so the energy of the original orbit, and incidentally, you don't really need this, but we're going to get an expression for how much energy you had to expend to slow down. Okay, I didn't ask for that, but let's go ahead and do it. And right now, we're just trying to frame the problem because when I posed the problem, people had an awful hard time getting started. Okay, so the energy of the original orbit is what? Well, square the velocity, get gm over r, multiply that by 1/2 m, and there you have it. Okay, potential energy okay. You know, I kind of garbled that last time, so let's just quickly derive the potential energy at distance r. So here's the mass big M. Here we are at distance r. Relative to infinity, which I'm going to say is just very far away, far enough away that the difference doesn't make any, the difference is negative. Okay, so from very far away, we'll call this distance r/2. If we go from here to here along a straight line, it doesn't matter whether we go along a straight line or something else because gravitational force is conservative. So to get from here to here takes a certain amount of work against the gravitational field, no matter what our path. Okay. Take a little increment. Delta r, distance r star. Gravitational force dotted with delta r. Well, this is a radial path, so it's just a product of gravitational force with delta r, and it almost looks like I've got a fraction r star over delta r there. Okay, F grav times dot delta r. Okay, well, F grav is this way. Delta r is that way. So this is negative big G, big M, little m over r squared delta r. That leave myself enough room here, so I'm just going to start doing the potential energy here. I'm going to do it by the integral and reason it out. Now this is r squared. It should have been r star. That might be hard to read, but whatever this sample distance is within this increment. Now you did this in calculus. You did sums, limits, and all that stuff. Okay. So I'm just going to say the sum of all the f graphs times delta r. You just, break this up into limited increments. Approaches the integral from little r to r half of negative big G, big M, little m over r dr, which equals big G, big M, little m over r hat minus big G, big M, little m over r. That's such a nice r. I hate that to it, but I'm going to have to put it there. Okay. This approaches as I'm writing that too small, but I didn't know I was going to have to do this. This approaches as r hat approaches infinity. This approaches zero, right? As r hat's in the denominator and it gets making everything else get small. So that's just negative big G big M, little m over r. Now that's the work done by gravity from here to here, or from here to infinity, right? So what's the change in the gravitational potential energy? What's your conclusion? What principle do you use to figure out what that change is? After a long digression, to remind people of my paradigm example, lift a cinder block, potential energy goes up, gravitation. You can tell it goes up because if you release it, it falls. Okay, if you lift it up from your feet all the way up here and drop it on your foot, you really know that it fell. Don't do that. Even if you got steel toes and metatarsal guards, still not fun. It might nick your shin too. Okay. You probably want shin guards, might take your kneecap off if you're not careful. So, don't do it. Don't be lifting a cinder block and dropping it near your feet. Okay. Point is, potential energy goes up when you do work against gravity, meaning it goes up when gravity does negative work, and gravity does negative work because your motion is this way and the gravitational force is this way. the dot product of those two things is negative. Okay, really lock that in. It's going to come up again and again in more second semester than first. So work done by gravity is this: change in potential energy from the example I just gave you that you really want to understand and always think about, unless you got a better one that you make up yourself, that's even better. Okay, it's equal and opposite to the work done by the conservative force. So potential energy is okay. Well, I have a digression there, but we're not even done because we've got to talk about the fact then that potential energy is going to be measured with respect to infinite distance, because everything has a position relative to infinite distance, okay? And that's the most convenient point to use because we just get this simple expression. If we wanted the potential energy relative to some distance r hat, we'd have this, okay? Which is more complicated than this, or this. Okay, we'd have a negative here and a positive here if we wanted the potential energy. Okay, this is the work done by gravity. If we want it relative to the surface of the Earth, then or the surface of the planet, then r hat would be the surface of the planet. We'd still have two terms. Here we have only one term. Okay, so potential energy is always negative because anything, no matter where it is, falls toward this mass, right? And gravity does positive work on it, meaning that the change in potential energy is negative. You start from infinity, gravity is doing positive work, you change potential energy is negative. Okay, here we integrated from this position to infinity. If you want to change in potential energy relative to infinity, you integrate from infinity to r. Okay, and you get just the opposite of what you got here. All right, so sort that out. You really want to have that sorted out. I mean, I had a lot of confusion with atomic structure changes in atomic orbitals because I never did have straight why the potential energy was always negative. I didn't really have the perspective, and it's a simple enough perspective when you work it out. Okay, we might not do that much with atomic physics, but we will have. We study electricity and magnetism. We're going to do those things. Okay. Okay. Well, there we are. And we still have a little confusion. Why infinity? Because you can't actually get to infinity. And you don't want to. I've been there. It's still. You never get there. Okay. Well, you take a limit as you go to infinity. This is how you calculate an integral to infinity. I mean, I implicitly did it here. This approaches this, which is this. And then as r hat goes to infinity, there is your integral from here to infinity. Okay. Now, first place, you would have to admit that your integral from infinity to here is going to be the negative of that. Okay. And that would be potential energy relative to infinity. Now, you say relative to infinity. Why relative to infinity? Since you can't ever get there. Well, infinity is basically any place that's so far away you have negligible work from there to actually get to infinity. Okay. So, and think just very, very far away to where the difference makes no difference, to where the difference is negligible. Okay. So It's just the integral from a point very, very far away. And since the gravitational force drops off is the square of the distance, you don't have to get all that far. You know, go out to the orbit of Pluto and figure out what the potential energy is with respect to the Earth, okay? And then integrate it to infinity, you're not going to see much difference. In other words, the integral of this expression from distance Pluto's orbit to infinity is very tiny. And I should have had an R squared here because we're integrating this way. I mean, if you integrate the reciprocal R, you get a natural log, which would be a disaster. Natural log goes to infinity. So you don't even end up with finite energy. So that'd be ridiculous. Okay. So anyway, there we have it. And we will see a place where we have to integrate 1 over R for the energy, an infinitely long charged wire. Interesting case. That comes up in a couple of months. Okay. So this is a big deal. There is the expression for our energy relative to infinity. So now we can get the energy of the orbit. Okay. Which will be the kinetic energy plus the potential energy. So all this aside, here up to here. The total energy is negative big G, big M, little m over 2R, which we did last time. Okay, give you a little more explanation this time, especially since you asked for it. Okay. Now, all that is a foundation for understanding orbitals. There's more to it. There's conservation of angular momentum and stuff. Okay. We're going to need to address that. Now we see that circular orbit velocity is square root of big G, big M over R. Now VI is going to be less than that, so you're going to end up down here. And this radius is R. This distance is going to be A. Okay, well, I mentioned angular momentum. Let's think for a minute. Do you remember what I told you about why the angular momentum in any orbit has to be constant? I kind of waved my hands at it. I don't expect, I'm just over. Anybody remember me talking about that? Remember me mentioning it? Okay. You probably didn't lock it in. I wouldn't expect most people to lock it in. Okay. If I had a class of 50 people, it'd be 2 or 3. might be crazy enough to lock it in at that. Okay. It's simply because at any point in this elliptical orbit, the force is toward M. Okay. Well, how much torque does a force toward your axis of rotation produce? Your moment arm is zero. So angular momentum can't change. There's no torque. So and L, if you're reading your book, you know that that's the symbol they use for the angular momentum. If you don't, that's a symbol they use for the angular momentum. Okay. And so I'm using it too, because I don't want to have to keep writing out all the words. Although I like to write the words early on because it's important. Make everything symbolic too soon, and you totally lose any connection with reality. Okay, anyhow. And then you got to rebuild it. And that's worth doing. So, okay, you know, L. Gravity exerts no torque. About the force of the gravitational force. That's an abbreviated statement. By the source, I mean the source of the gravitational force, the source of all the force here. Okay. I'm thinking of theme song to Mr. Ed. Has anybody ever thought of Mr. Ed? It's a television show 7 years ago. 6 years ago. Okay. Horse is a course. Horse is a horse, of course, of course. No one can talk to a horse, of course, unless, of course, that horse is a famous Mr. Ed. So when we talk about the source of the force, naturally, Mr. Ed pops into my head. That also. Okay. Yeah, you want to have crazy stuff running around in your head because sometimes it's useful. That wasn't. My point is, there's more words for the source of the force, etc. Okay. I hadn't thought of that jingle, but it'll never go out of my head. It's 60-some years old. Okay. We understand that idea. Angular momentum has to be the same. What is the angular momentum? Angular momentum is MVR or M omega, since V times R is omega, right? And what's omega? Omega is the rate at which the angle here is changing. So if I had two positions here, the angle I was about to say something stupid. So, okay. This is there's an angle theta, which is omega delta t. Omega being the rate at which your theta is changing, right? We've been familiar with that since the first day of class. Okay, so we have this. is equal to mvir, which it was as soon as we slowed down to vi, okay? So here we slow the velocity v sub I to go into the elliptical orbit. Now we know a lot of things about this orbit. I'm claiming it's elliptical. I haven't proven it and probably won't. You'd have to know too much about conic sections to relate to it. Because that probably would be worth the time. Will can tell you if you want to know, ask me. But outside of class. Okay. What do we know about this situation? Now we know the total energy. Negative big G, big M, little m over 2r. Well, that's the circular orbit. After we slow down, it changes, right? So let's be sure we get this well. In the circular orbit. Okay, well, what then is the total energy of the elliptical orbit? I'll say E circular to distinguish it from the total energy of the elliptical orbit. The total energy of the elliptical orbit. And I would say, find the energy of the elliptical orbit at this point. Okay, so the energy of the elliptical orbit isn't the same as for the circular orbit. Okay, and it depends where you are. Well, no, it doesn't depend where you are, what the total energy is. The potential and kinetic energies change as you move around this orbit. But the total doesn't change because the only force acting on this thing is the gravitational force, which is conservative. Excuse me. Yeah, well, we know that the thing reaches this point in the elliptical orbit, so that at this point, we know the potential energy. Negative of big G, big M, little m over r. And then the kinetic energy is easy. We slowed to VI. There it is. Okay. So elliptical orbit, it equals this, right? Well, what's its potential energy? What is its distance A? It's I'm going to say it's big G, big M, little m over A, negative big G, big M, little m over A, plus 1/2 m times the maximum velocity squared. Maximum velocity occurs here because the minimum potential energy occurs here. Okay. As you start moving away, you start losing potential energy. From further away, you lose potential energy, move closer, you gain. So from here to here, you're losing potential energy. Therefore, you're gaining kinetic energy until you get to this point, and then you start moving further away and you start gaining potential energy, thereby losing kinetic energy. Did I say that right? Gaining potential energy, losing kinetic energy. Okay. So, well, here's an equation then. How many unknowns does it have? You move your fingers. What's unknown? What's not specified in the problem? Well, there are 5 variables, but they're not all unknown. Big G is known, big M is known, little m is just whatever mass you decided to make. That leaves you only A and V max. Those are the only things you don't know, assuming you know everything that was given. Okay, so there's only 2 unknowns. So we're going to be able to figure this out if we just have another equation. Can anybody find another equation from something that's on the board staring at you? Okay, well, the other thing is, again, just from the principle again, that you can't exert a torque with a gravitational force. You can't exert a torque about the point source. Okay, if the axis or the point of rotation is the source, you don't get a torque. So the angular momentum has to stay constant. Okay, so can you write an equation that tells me that the angular momentum is conserved? You got one expression for the angular momentum. Can you write another one in terms of unknowns? A, V max. The angular momentum at this point going to make this orbit purple, so then anything I write in purple refers to this orbit. Okay, it was mvr. V was this, right? So it'd be the square root of big G big M times R. I think. Can't trust my head. Okay, down here. L is mv max times A. Okay, it's just your relative position vector times cross with your angular momentum or your mv. Okay, your linear momentum. Okay, so we have an equation. Okay, if you want to solve for A, then you solve this equation for V max and substitute it here. What do you get? Well, it's just a simple exercise in algebra too. Okay. Which I'll probably mess up. I don't know if you can read that. R's are hard to write. Had a pull, then you push. Got to optimize my strategy for writing R's low on the board. Okay. You just solve this for Vmax. You're going to divide by MA. M's going to divide out. You're going to end up with an R over A and a VI, right? And that's just a ratio. Okay. So many times further this is than this. Okay. So in accordance with Kepler's law that says you sweep out equal areas in equal time, since you're this much closer, you got to be moving this much faster to do that. Think about that. Okay. So your elliptical energy is negative big G, big M, little m, over V high times A over R. And what do? I just substituted the expression for V max for A. I got something that I was wondering, what in the world does that mean? Doesn't mean anything because I messed up my very simple algebra. Okay. The elliptical is negative big G, big M, little m over A, which I started to write down. Wait a minute. Yeah, okay, that's right. Well, I don't have room to write out the entire solution. You got this, right? And you set it equal to this and solve for A. It's going to be quadratic in A. We're going to get two solutions. So you get worked out. And the point is, this is a solvable problem, but it's a little more complicated than you might think at first. Okay, which is why you kind of go through it. You figure out what you can about the circular orbit. You get the total energy. You come over here and you get the total energy from the elliptical orbit. That's not difficult. Okay. Then the difficult thing is you think, gosh, that leads me to an equation because I know energy is conserved. Of course, you got to have energy conservation in your mind, which hopefully you do after what we've just been through in the last couple of chapters. Okay, so you write out the energy conservation equation, then you say, gosh, I've got two unknowns. What am I going to do? Well, I just wrote it out for you. Angular momentum is constant, so you can solve. I'm not going to go any further with it. I really, I mean, it's easy enough to write things out and be careful to do your algebra. So if you really want to, you're out there orbiting a planet and you want to approach within 50 kilometers, hopefully the planet doesn't have a whole lot of atmosphere if you're going to get that close. Okay. Now we did that last year with the Orion probe. Okay. And I spent a lot of time over a few days trying to figure out just what they were doing with that thing from the telemetry data. Okay. Pretty interesting situation. They overshot the moon, and then they made a pass near the moon, like where if you had just an average rifle and were a good shot, you could probably shot it. Okay, it was close. You would have seen it. Maybe not well enough to get a beat on it. It wasn't that big. You know, that's probably going to send people in. They want to see what's going on. People deal with this. Can they survive this? Can they do this? Okay. Very interesting. So they made a very close pass to the moon. So they had to calculate this. Okay. Had to test it out to make sure their calculations worked. And of course, with those calculations, they also had to take account of Earth's gravitational field, which was dominant until you get pretty close to the moon, because the moon's much less massive. So it's very, very interesting three-body problem. But that's kind of the fundamental thing they looked at. They had to throw Earth's gravity into, which really complicated things to make it go where they really wanted it to go.